Welcome everyone to section number 6, Measurement System Repeatability. Repeatability is the measure of how repeatable our measurement system is. A measurement system is repeatable when it consistently gives us the same reading over and over again. Imagine that you have a ruler, okay? So you have a ruler right here, and we ask an inspector, let's say Carlos, to measure a 2-meter long part. His readings are the following. First sample, 2.03. Next up, 2.09, 1.99, and so on. The important thing to note here is that Carlos is measuring the same 2-meter long part each time, okay? We're not mixing and matching. So the variation that I'm seeing part to part is actually from Carlos using the ruler differently each time, okay? Now I can grab this information right here, as we've been doing before, and we can calculate for bias. So we're simply going to do stat basic 1 sample t. I'm going to grab C2, and I'm sure that the gauge block or sample that I'm using is exactly 2 meters long. So we'll do a hypothesis test for 2 meters. Now from here, I can do an analysis of my p-value. If I look at my p-value right here, I'll notice that it is above 0.05. Since it is above 0.05, that means that my system does not have bias. So no bias in the system, right? I can also see that the overall mean is 2.01. Okay, and the confidence interval contains the value of 2 between itself. All of this should be familiar to you guys. If the topics that I'm discussing are not familiar, please review the previous sections where we discuss bias in length. Now, after confirming that the system is not biased, we must still determine how consistent is Carlos when measuring. So we know that the p-value calculation tells us there is no bias in the system. However, just by looking at the results, 2.03, 2.09, 199, 199, and so on and so forth, we can evidently tell that Carlos is not exactly getting the value of 2. This variation is coming from the exactly same part. So we expect Carlos, if he was perfect, to always get 2 meters, 2 meters, 2 meters, and so on and so forth. This is known as repeatability. The fact that people can't get the same result over and over again is going to provide us with a repeatability value, which we can identify mathematically as the standard deviation from our measurement system. Mathematically speaking, standard deviation is the mathematical calculation of how much the results vary from the nominal value. The formula for standard deviation is shown below. So we have this section right here. This value is known as the standard deviation, also called sigma. It's based on the square root of the sum of xi, which is each individual value, minus the mean of the overall values, divided by n minus 1. Now, please note that you do not need to do this calculation by hand. The program does it for us. But we want to introduce the concept of repeatability so that students understand that it's not just making sure that my system is not biased toward giving me parts that are small or big, but my system must also be consistent in that I must consistently get the value that I'm looking for in real-world conditions. Please note that this formula for standard deviation uses the value n minus 1. This is known as the sample standard deviation. If you Google the formula for standard deviation, you might find this formula right here. It looks identical, except that instead of n minus 1, it simply says n. This is because this is known as the population standard deviation. In most statistical calculations, since we're doing sample sets, we don't have enough data to infer population, the formula used is n minus 1 because we're taking into account a small degree of uncertainty because we don't have that many samples. Okay. Now, we don't need to do calculations by hand. We can simply ask Minitab to do the calculation for us with stat basic statistics and display descriptive statistics. So if I were to take my original data, which is shown right here, I simply do stat, basic, and display. I can ask for the C2 column, which is the one that has my data right here, And here on statistics, by default, there are a couple ones that are already activated. I'm gonna deactivate pretty much all of them, except for the mean and the standard deviation to make it easier for students to visualize the results. So what Minitab is telling me right now is that if I grab all 10 samples and I average them together, the mean is going to be 2.010. Okay. And if I calculate by hand the standard deviation is going to be 0.0469. Okay. Now, what does it mean to have 0.0469 standard deviation? We'll get into that in a moment. For now, please just identify the tool that allows us to do this, which is stat, base statistics, and display discrete statistics. From here, we are now going to look at the standard deviation. There's a handy rule in statistics that allows us to determine the overall variation that a person or process will generate. We call this the mean plus minus 3 times the standard deviation will provide us with the overall process width. In this scenario, the mean is 2.010 and the standard deviation is 0.0469. Okay, I'm gonna make this a little bit thinner. If I were to multiply this standard deviation by 3, okay, I would get 3 times 0.0469 provides me with plus minus 0.1407 plus the mean, which is 2.010, and my overall range is this one right here. What am I actually saying? I'm saying that if I keep asking Carlos to measure this exact 2-meter part without changing the part, just giving the part to Carlos over and over and over again, I expect his results to be between 1.86 meters and 2.16 meters. Is this significant or not? We'll get into that in a moment. For now, please just be aware that this rule is very useful in statistics and we use it constantly. The mean plus minus 3 sigmas or 3 standard deviations is about 99% of all the data results that we expect to get from Carlos when he measures the part. So let's do the same calculation again and let's review my data. Is the data within the range that I have mathematically calculated between 186 and 216? 203, yes, it is within the range. 209, yes, it is within the range. 199, yes. 206, and so on and so forth. As you can observe, based on my mathematical calculation of the mean plus minus 3 sigma, all the data points are within the expected values. So the rule has been met. We call this rule the 3 sigma rule. For any normal process, the measurement results will always fall around the mean plus minus 3 times the standard deviation. Visually, it will look something like this. So I have my mean here in the middle, and I expect most of my data to fall within this range of 3 sigmas toward the right and 3 sigmas toward the left. That is around 99.73% of all data results. There are a couple of stragglers shown here and here, but in statistics, we don't really worry about them. Most of my data is already contained within this rule. Within plus minus 3 sigmas of the process mean will be 99.73% of my data. If I take this information over to my part, it means that a part that measures 3 meters, for example, based on Carlos' existing standard deviation. So let's say give Carlos a part that is 3 meters long. That will be a mean of 3, real world condition. And Carlos currently has a standard deviation of 0.0469. Carlos might tell me that that part is as big as 3.14, or he might tell me that the part is as small as 2.85. I could then wait, let's say 1 or 2 hours, and give that exact same part to Carlos, and Carlos might tell me that the part actually now measures 2.95 with this, which is within this range. And then I can wait another 30 minutes, and then Carlos is going to tell me the part measures 3.05 and maybe 3.10, and I can keep going. But Carlos will never exceed this range. That is his 3 sigma standard deviation range based on the real world part value. Okay, so the real world part is going to be here in the middle, and Carlos' range is going to be toward the right and toward the left side of the real world nominal value. This might sound complex, but please don't worry. We're going to do a couple of exercises, and the topic should be more familiar to you guys as we do the exercises. So stay tuned.